Okay, so now we're going to talk about subgames and subgame perfect equilibria of infinitely repeated games. So if you imagine an infinitely repeated game as a tree, so this is kind of we branch for every round we keep branching, and then this just keeps going to infinity. So the tree keeps going and gets bigger and bigger. If you think about what subtrees are, is basically that at every node that's like the first node of one of the stage games, we can take the subtree from that point. So those things are really specified by the finite list of plays up until that point. That tells us how to get from the root to where we are right now at the beginning of some stage, some copy of the stage game, together with the root, which tells us the history of plays up until this point. Now, after that point, of course, there's still an infinitely repeated game, right? If you're playing an infinitely repeated game, then cutting some finite number of stages off the front doesn't change the fact that it's an infinitely repeated game. But really, the subgame we get here, there's a kind of self-similarity that the subgame that we get here is really a copy of the original game, except that we've transformed the payoffs by an affine function, where we are multiplying by a bunch of copies of the discount factor and then adding the finite amount that we got from the play up until that point. And given that positive affine transformations don't change anything, that means that essentially every subgame looks kind of like the game that we started with. So this is an amazing fact about infinitely repeated games. So this is not true for any finite game, because of course, when you take a subgame of a finite game, it has to be smaller than the original. But in an infinitely repeated game, this is no longer the case. Subgames don't have to be smaller. So what subgames really are is that they are the same thing as finite lists of moves up until some particular stage. What that means is, so if we want to use the one deviation principle to check whether a strategy profile is subgame perfect, we would still have an infinite problem, because we still have an infinite set of subgames, namely all of the possible finite lists. There are infinitely many of them. But now is where we get the benefit from having restricted to finite state strategies, because a finite state strategy will always do the same thing in any two subgames that take it to the same state. So what this really means is that subgames really become like combinations of states of the strategies that you're in. So this brings us to a finite problem. We only have to check that the optimality conditions are going to hold for every combination of states that the strategies could be in. Because of this self-similarity, because the subgame looks like a transformed version of the original, what this really means is that to check whether a strategy profile is a subgame perfect equilibrium, all we have to do really is to check that it's an equilibrium for just the start, just the first stage, but for if you replace the initial states of the strategies with any possible initial state. Okay, so let's say we want to play tit for tat versus itself. And let's say we want to, so this is a subgame perfect equilibrium of iterative prison's dilemma, as long as the discount factor is high enough. So let's verify this. So there are 4 combinations of states, because each of these strategies has 2 states. So if we combine these, we get a kind of coupled state machine. And we can see, because we get 2 state machines that essentially react to each other, so we can just make a kind of transition system here. If both are in the cooperate state, they're just going to loop back on itself, because they're going to copy each other. If both are in the defect state, they're going to stay in the state, which is going to loop around in the same state. If we're in the other 2 states, defect cooperate and cooperate defect, they're going to flip-flop. Now, what we can do is that for each of these four states, we can work out the payoffs that both players get from being in that state. So let's say if we start in state CC, so this is the actual true start state, then the total payoff for both players, we're going to get 2 in every round. So we're going to get 2 times the sum of this infinite series, which is this thing. And if you plug in a particular discount factor, you can get the actual answer. Now, some of the other calculations are a bit more tricky. So let's say we start in state CD. So that's this one. So we're going to flip-flop between. As we unfold the play, we're going to flip-flop. So what that means is that, so let's say we want to get the payoff for player 1. That means that in the odd numbered states, player 1 is going to get a payoff of 3, and for the even numbered states, player 1 is going to get a payoff of 0. Is that right? I might have got these the wrong way round. There is a definite possibility that I've got these exactly the wrong way round, but it doesn't significantly affect things. Okay, let's pretend I got this right. So we want to sum up this thing, and here is where you have to kind of remember very old math tricks for using infinite series. So I'm going to do a bunch of re-indexing. So this thing is 0 on the even indices, on the even I. So I can re-index by replacing beta with beta squared plus 1 or beta squared minus 1, and then do a bunch of re-indexing. And I hope I got this right, because I haven't thought about infinite series in an extremely long time. And if I didn't make a mistake, then you get this answer. So in theory, if we want to verify that tit for tat is a subgame perfect equilibrium, we're going to have to do this calculation for both players in each of the 4 states. And if we don't make a mistake, then we will find that. So, okay, so I skipped a step here, which is that in each state, we have to check that this is higher than the payoff that player would get if we did something else, if we kind of deviated from what the state machine says just in the first round. So we kind of jump somewhere and then follow the state machine after that. So we have to do even more of this kind of infinite series calculation. And the one deviation principle says that this should be subgame perfect precisely when the thing that we get from following the strategy profile, the thing that every player gets from following the strategy profile, is at least as high as what they would get from deviating in the first round. And if we run all of these calculations, we will find that this is in fact the case as long as beta is high enough. If beta is very small, then this can fail. If beta is small, it means the players are very impatient, so it can become better for them just to defect in the first round and then take the punishment after that. But if beta is high enough, then we will find that this is a subgame perfect equilibrium. You see, these calculations are not so easy. Even though I've done everything I could to make it as easy as possible, these calculations are still kind of tricky. Okay, now I've given you quite a lot of examples of subgame perfect equilibria for infinitely iterated Prison's dilemma specifically, like all of the combinations of tit for tat, grim trigger, any amount of finite punishment, and also always defect is another one. There's a general principle that say this is simplified to the point where it's inaccurate, but there's a slogan like in an infinitely repeated game, practically everything is a subgame perfect equilibrium. To be more precise, almost anything almost any payoff can be the payoff from a subgame perfect equilibrium. And to be even more precise still, any reasonable combination of payoffs, where I'm going to define what this means on the next slide, can be the result of playing some subgame perfect equilibrium as long as the discount factor is high enough. And there are theorems which are called the folk theorems for slightly historical reasons, which make this precise. So this gives us a kind of framework for proving that certain outcomes like cooperation can happen in an infinitely repeated game without having to go through all of these nasty calculations. We can kind of use one of these theorems as a black box. On the flip side, what this means is that infinitely repeated games fail kind of badly as a predictive theory because they sort of say anything can happen, and they don't rule things out. Okay, there are several related results along the lines of the folk theorem. So this is the most straightforward one. This is for infinitely repeated games with geometric discounting and subgame perfect equilibrium. So there are versions for each of those words being changed. So what the theorem says is that any combination of payoffs is going to be the payoff that results from some subgame perfect equilibrium, as long as the discount factor is big enough, provided two conditions hold. One is called individual rationality, which says that for each player, the payoff in question, that's the one that we're trying to say results from some subgame perfect equilibrium, must for each player be at least as big as their min-max payoff in the stage game. If it's not, then the player would rather play their min-max strategy. And the other is called feasibility, which is kind of straightforward. It says that the payoff has to be a convex combination of payoffs in the stage game that you can get from pure strategies. Otherwise there is no possible strategy profile that will reach it.